All right, welcome to The Explainer. Today, we're going to break down a huge topic. We're going to follow a machine learning model on its pretty wild journey, from just being code on a laptop to becoming a real, reliable service that millions of people can actually use.
So let's kick things off with an idea that catches a lot of people off guard. You know the cool part, training a model to make these amazing predictions? Well, that's really just the tip of the iceberg. The real challenge, the hidden 80% of the work, is all the engineering that has to happen after to make that model useful in the real world.
So to really get a handle on that hidden 80%, we're going to follow a model's journey through 5 supercritical stages. We'll start with getting the data right, then move on to launching the model safely, scaling it up to handle tons of traffic, keeping an eye on its health, and finally, making sure the whole thing doesn't break the bank.
Okay, so every model's journey starts with its fuel, right? And that's data. But right out of the gate, there's this really common and dangerous problem that can pop up. One that can kill a project before it even gets off the ground.
This problem has a name. It's called training serving skew. Just imagine this. You train your model using data you processed one way on your laptop, but then when it goes live, the real-time system calculates that exact same data just a little bit differently. That tiny difference can cause a model that seemed like a genius in the lab to fail spectacularly in production. It's honestly one of the biggest reasons why models fail. So how do we fix this? Well, the industry came up with a really smart solution called a feature store. Think of it as the single source of truth for all your data. It has 2 main parts: a massive offline store with tons of historical data for training your model, and a lightning-fast online store that serves up the very latest data for live predictions. This guarantees the exact same logic is used in both places, and bam, no more skew.
Okay, so we've got our feature store. We're feeling pretty good. But wait, there's another really sneaky trap we have to watch out for, called data leakage. This is when your training data somehow includes information from the future, basically giving your model the answers to the test before it even takes it. It makes the model look way smarter than it actually is.
And this slide really breaks down just how easily a model can, well, cheat. Let's say a fraud event happens at 10 a.m. sharp. But to train our model, we accidentally used some data that was calculated 5 minutes later, at 10:05. We've just taught our model to predict the past. It looks like a genius during training, but it's totally useless in the real world where, it can't see 5 minutes into the future.
All right, so our model is trained on good, clean, correct data. What's next? Well, it's time for it to leave the nest. We have to package it up and turn it into a real network service that other applications can use to get predictions.
We do this using special software called serving engines. You can think of them as supercharged web servers built just for machine learning. And you've got options. TensorFlow serving is like a V8 engine. It's a C++ powerhouse for TensorFlow models. NVIDIA's Triton is the Swiss Army knife. It can handle all sorts of models and is amazing with GPUs. And TorchServe is perfect if you're using PyTorch and need to write a lot of custom Python code.
But here's the thing. You can't just flip a switch and send all your users to the new model. What if there's a bug? Yeah, that would be a total disaster. So we have to be smarter about it. And a classic strategy here is called the canary deployment.
And here's how it works, and it's pretty brilliant. You start by sending just a tiny slice of your traffic, like just 1% to the new model. You watch your dashboards like a hawk. Are errors low? Is everything fast? If it all looks good, you slowly turn up the dial, 10%, 50%, until you're finally at 100. This whole process limits what we call the blast radius if something goes wrong.
And that's not all. There are a couple other really cool patterns too. With shadow deployment, you send real traffic to your new model, but you don't actually show its answers to users. This lets you test it under real-world pressure with zero risk. And the sidecar pattern helps keep your code clean by moving stuff like security and logging into its own separate container.
Okay, so our model is live, it's safe, and now we've got a great problem to have. It's a huge hit. Traffic is going through the roof. So the big question is, how in the world do we keep it from falling over?
The answer to that question, pretty much across the entire industry, is a system called Kubernetes. The best way to think about it is as the operating system for the cloud. It's designed from the ground up to manage applications that are packaged in these things called containers and to make sure they run reliably, even at a massive scale.
So Kubernetes has these core building blocks you need to know. Your model runs inside something called a pod. Pods run on nodes, which are basically just virtual machines. A service acts like a traffic cop, making sure requests go to the right pod. And a deployment is where you tell Kubernetes what you want, like, hey, always make sure I have 3 copies of my model running, okay?
But here's the real magic of Kubernetes.
auto-scaling. And it happens at two levels. First, you have the horizontal pod autoscaler, or HPA. It's the fast responder. It watches for things like high CPU and can launch more copies of your model in just a few seconds. Then, if you start running out of physical machines, the slower cluster autoscaler kicks in and adds brand new machines to your fleet, giving the HPA more room to work its magic.
So you might think we're done, right? The model's deployed, it's scaled, time to celebrate? Well, not so fast. In a lot of ways, the real work is just getting started. We now need a totally new way of monitoring to make sure our model stays healthy.
See, with normal software, it either works or breaks. You get an error. It's pretty simple. But machine learning systems, they can fail silently. The code can be running perfectly with zero errors, but the model could be giving out complete and utter garbage predictions because the world has changed around it.
So that means we have to watch for totally different things. We track data drift, where we ask, does the live data coming in still look like the data we trained on? We look for prediction drift to see if the model's answers are starting to look weird over time. And we have to deal with ground truth lag, which is the often very long delay between making a prediction and actually finding out if it was right or wrong.
And finally, we get to the part that makes everyone nervous, the bill. With our model serving millions of requests, all this amazing infrastructure costs money, a lot of money, and we absolutely have to manage that cost.
And that really boils down to one simple but incredibly important question that every team needs to be able to answer. How much does one single prediction from our model actually cost us? We can't just get a giant cloud bill at the end of the month. We need to understand the unit economics of what we've built.
This is where a whole new field called FinOps comes into the picture. It's all about bringing financial accountability directly to the engineering teams. It empowers them to make smart trade-offs between, say, the speed of the model, the cost to run it, and the quality of its predictions.
And this stuff really, really matters. Why? Because smart engineering choices can have a massive impact on the bottom line. For example, by using something called spot instances, which is basically just spare cloud computing power sold at a huge discount, you can slash your costs by up to 90%. 90%. That is a total game changer.
So when you look back at this whole journey, from getting the data right to deploying, scaling, monitoring, and managing costs, it really forces you to think differently. It leaves you with one final big idea to chew on. A great model isn't some static asset you just build once and forget about. It's a living, breathing product that needs constant care, investment, and infrastructure to be successful for a long, long time.